Okay, so I'm Katie, and I'm going to tell you a little bit about my honors in the major project for mathematics. So we're going to start out with what is pure math research. So the goal of pure math research is to prove that a statement is either true or false. And the way that we do that is with something called a proof, which is a logical argument. So you may have seen something similar in philosophy. And this begins sort of the way that scientific research begins. So you pick something that you want to study, you do a lot of background reading to see what is already known about it, and then you formulate a hypothesis. And then from there, rather than following the scientific method of a set experimental procedure, it becomes sort of a creative process. Every question is different, and so you have to go on a little bit of a case-by-case basis and figure out how to answer this specific question. So there are a couple of different structures that proofs commonly take. The two that are used most in my project are explained a little bit here. So the first method is called a direct proof. And this is something we start with the definitions, and then we go from simple logical deductions from statement to statement until we arrive at the result that we want. And so there's a short example of what that looks like here. And then in a proof by construction, if we're trying to prove a statement that's of the form, there exists some object that has this property, we can prove that by finding such an object and demonstrating that it has the property that we want. And there's an example of a proof that looks like that here. So for my project, I studied objects called algebraic curvature tensors, or ACTs. And these are tools that we use to study the curvature of a manifold at a single point. So there's an example of a manifold here, this picture that I have. This is an example of a two-dimensional manifold, but you can have manifolds of any dimension. And ACTs are kind of a useful measure of curvature because they're pretty easy to work with in comparison to some other measures of curvature. Each ACT has an associated quantity called a structure group. And for our project, we hypothesized the structure groups would behave in a specific way. And so our hypothesis is up here, and we just hypothesized that they would behave this way, except on a very small set, or so almost all of the time. And so the results of this project where I used a direct proof to show that our hypothesis is true for ACTs that represent the curvature of either one or two-dimensional manifolds, so things like you see in this picture here. And then in the three-dimensional case, I showed by construction that there are more examples of ACTs that behave in a different way from the hypothesized way than we had originally anticipated. And so because our hypothesis includes this almost always criteria, the hypothesis wasn't disproven, but it does kind of show that there might be more to the story than we had originally anticipated. So that opens some avenues of future work that could be done on this topic.